Some people have been asking for what are we going to do at the end of the day. So I have no plans for it. So I thought that we could just have some beers here, or we can go somewhere. So think about it, and if you want to join, at the end we will do something like a friendly meeting to continue a little bit with our discussions. So I think that will be all the announcements for now. There is one more coffee break. Yes, so we are fine. Now we restart the conference with Gonzalo Gutiérrez, our keynote speaker from University of Chile, Faculty of Physics, which is actually almost across the street. That's why we have so many people from University of Chile, which, by the way, is like the biggest university of Chile, together with Catholic University, the BUC, that we have Professor Mace yesterday. So that's a good indication for this conference. We have people from the best universities. So that's really good. So Professor, please, Gonzalo. Important thing to speak to the microphone, because otherwise it's not, the signal will not get to the future.
Okay, thank you very much for Ifik and Tomás for inviting me to talk today. I'm going to talk about this maximum caliber principle, which is in some way it's a pointer here?
Yes.
Which one?
It should work. El botón rojo era...
Okay, yeah. It's more or less similar to the maximum entropy principle, and this is a work that we are doing with Sergio, who is here in the audience, and Diego González, a PhD student just graduated. We are a group which work in material physics from an atomic and molecular approach, DFT, molecular dynamics, etc., and also foundation of statistical mechanics. So, because I have more or less 40 minutes, I think I would like to tell you some history, how we go to foundation of statistical mechanics from something such concrete as material physics. Well, it's about the following. We wanted to simulate a spin system. We work in molecular dynamics. Molecular dynamics simulation is just to simulate an atomic system, but the atoms are particles, and the interatomic force could be some functional form of the force, like the Lennard-Jones potential, or you can have this force from first principle, ab initio molecular dynamics, from quantum mechanics. But in principle it's very simple, just to solve the Newton equation, and the temperature of the system is related to the kinetic energy of the particles. So the equipartition theorem is well known in the first years in physics and engineering, so that's no problem. But then we wanted to simulate spin system or magnetic system, like the magnetic moment of the particles in a continuum spin, so not discrete, but a magnetic moment that can have move in all the sphere. And the problem was the following: how to assign temperature for a magnetic system, because I am going to explain what was the problem, and we think that we solved this problem. That is what I'm going to show you, and then I'm going to do this maximum caliber thing. Well, in a dynamical system, this is the typical form to assign temperature, but also due to Rook, and we extend this proof, we can assign the temperature also in this way, this is the Hamiltonian. The Hamiltonian is, for example, can depend on the variable, the momentum and the position. So this gradient here and this divergence here you can take this just from the momentum degree of freedom or from the position degree of freedom. So you can have some kind of configurational temperature too, if you take in account only the position of the particles.
¿Pasa?
Yeah,
¿Te pasa o no? Es que tengo que dar ahí. ¿Ahora?
Okay. Yeah. If you apply this formula to a Hamiltonian of this way, you get this expression. And you can see here we take the divergence with all the degree of freedom, the position and the momentum. But if you take only the momentum, then the temperature is related, is an average over the potential energy, as you can see here. And this would not appear, right? So that's no problem. In a particle system, the temperature could be related to the kinetic energy or to the potential energy, taking this derivative. What about spin dynamic? Spin dynamic, you can represent the spin dynamic or how the magnetic moment are in movement by means of this equation, which is the Landau-Lipschitz equation, which is first order differential equation. It's very easy to solve. This is the Hamiltonian, and then you can have the dynamic of the system. For example, if you have a spin chain, then the spin would interact, for example, by the Heisenberg Hamiltonian, and you can have this kind of Hamiltonian. This is nearest neighbor interaction, this is an anisotropy and an external field, right? So you can, let me see if this is work, maybe Thomas, you can, this is,
no, en la película.
It's not the head film, okay, yeah.
¿Queréis que la ponga? Do you want me to open the movie?
Yeah, just to see how you solve this equation, this and this, you can move all this.
Okay. I will solve it in the way I can now. I don't know exactly how it should be done.
This. So it's exactly like a potential, like a particle dynamics, but it's the movement of each spin, right? But if you want to simulate this system at different temperature, the problem arises how you can assign temperature to this system. Because the following.
Let me get you back to the...
Yeah, okay. Sorry.
Okay. And
Yeah.
now, yeah.
No. Okay, this is working here also. Yeah. So in many situations you would like to apply temperature or to measure the temperature in the simulation. For example, in this case, how to calculate the thermal conductivity of a spin system, right? Then you need to know which is the temperature in each part of the chain. So in practice, this would be very useful. And a typical Hamiltonian is in this way, and you can see that here there is no kinetic part, right? So the naive view to assign the temperature according to the kinetic energy here doesn't work. That's simple. So you have to see how to apply temperature. How can one associate temperature to a system. And this is a problem that already know the founder mother, I would say today, of this field, founder persons of this field. Okay, the temperature that corresponds to either is not readily apparent. Note that there is no equipartition theorem for the system. This is the first spin dynamic that these people did, right? So the problem is it's possible to generalize, to apply temperature in a magnetic system. Yes, it is, and we found a generalization of this equipartition theorem that allow us to put temperature or to assign temperature of a spin system. These are the two papers, and I will show you that. This is there are two, well, just to show you that there are two methods in spin dynamics. One is the Monte Carlo, and the other is this spin dynamic that you have to solve numerically this, but so far there was not a clear prescription how to obtain the temperature. But if you have this kind of system, this is a way to obtain the temperature. So look that it looks like similar to this Rook formula. This is the Hamiltonian, and you have to take this operation over the Hamiltonian, take the average over different configuration, and then you get the temperature. This is the formula which in a particular way has been also been obtained by Bourdin and Chaud, and we obtain a generalization for any system with constraint. And I will show you here an example. This is a XY Heisenberg model, classical. We put some temperature here which correspond to, in our unit, 2.75, and this part is 2.25. We put together these two parts, and we just want to see what is the temperature evolution. You know, in the case of water, this would be 50 degree, 20 degree, and the result is the average of that at some time. In this case, you can theoretically predict what should be the final temperature, the equilibrium final temperature. You have to take in account the different heat capacity of the two halves of the system, and it's more or less this the final temperature predicted theoretically according to the energy temperature diagram. In this way, you go from here, this energy, this is the energy, and then you take the average of the energy and go back to this point, 0.56. What happened now with the simulation? We did the simulation just to put the two systems together and see the evolution in time. And this is the result. You see, the bottom part of the system starts at 0.25, evolve to this temperature, this decrease the temperature, and after some time, this is time in real time, seconds or whatever units, go in equilibrium, and it's exactly 0.53 more or less. So this is a proof that everything is working. Also, if you decrease the number of spin, the time equilibration is shorter, and the fluctuations are bigger, so everything it's like in theory. And also you can apply some Newton Coulomb model. So we are happy. This method it's working for spin dynamic, and we apply this to spin diffusion in spin chain diffusion. So we put some temperature in some of these spins and see what happened. Let me see here. Although this is just a movie of what happened with an external field and what happened with the uniaxial anisotropy in spin dynamics. But the good thing is that you can measure the temperature in each of these parts. Even the potential mark the temperature for each spin, like people can measure the kinetic energy of each particle and according to that assign some temperature. So we apply this to heat transport in low dimension. I'm going fast in this part because I'm going to go to the other thing, but just to tell you that this is an important topics, how is the heat transport in low dimension. For example, here it's a paper in carbon nanotube that they put some temperature here in the middle at the beginning, and they see how this temperature of the disorder spread out, right? So here is the time, and it's in this way, and you can see in that way, and this that not follow Fourier law, etc., etc. Yeah, it could be ballistic, super diffusive, subdiffusive, etc. We did the same with the spin system, and we put temperature in some of the spin at the center and see how this spread out is in this way, and we are able to follow in detail this spread. This is in the case of an isotropic Heisenberg system. This is in the case of you put some external field, it's more or less the same, but see that this is not a diffusive regime because it's not a Gaussian. And in the case of anisotropy, you can this diffusion is not like in the isotropic state. More or less, it's the temperature it's maintained in the center. So this is some kind of thermal insulator, right? Okay, so the main thing in order to derive this formula for temperature in spin system was this conjugate variable theorem, and that we deduced, and thanks to this work we entered to the field of statistical mechanics, but moreover in foundation statistical mechanics. And this is more or less the background of the work that I'm going to show you now, right?
Shall I change?
Yeah, please. Okay, so let me go, let me put the time here. Okay, so the line of my talk is I'm going to refresh you what are the idea of equilibrium statistical mechanics and non-equilibrium statistical mechanics. Please forgive me, the expert. It is a general topic, right? And what is the meaning of this maximum entropy principle, and how this maximum entropy principle can be generalized for non-equilibrium statistical mechanics. And what happened, and this is the work that we are doing, and it's also a work in progress for different relationships. Okay. Equilibrium statistical mechanics, the general idea is to obtain thermodynamic property as an average over microscopic expression, right? For example, you want to know the energy of a system, and you have to put the expression, the microscopic expression of the energy, for example, the Hamiltonian, and to take this integral where this is the probability density distribution, right? Which is the main things of statistical mechanics. This tells you what is the probability for the different state of the system. So you have a system, we have some external constraint, and the allowed state are some of that state, and some states are more probable than other states, right? So this quantity, the probability distribution function, is the main thing, and if you have this, you have everything, because any thermodynamical quantity it's obtained as an average, ensemble average over in this way. So everything, it's okay. Now, how to obtain this probability distribution function? Well, there are several ways, or three main ways. One is this Boltzmann way that this is the textbook way that people use. It's you suppose that there is an equal a priori probability for the microeconomic ensemble. From them, and from this ensemble, you derive all other conditions with different constraints, right? The other is the Gibbs variational principle, that to work in a system with heat bath, and then obtain from there the probability distribution function, and from this ensemble to obtain everything. The other method is this Darwin-Fowler method, that you, with some you have to examine some function and you get the most probable state. And the other one is this maximum entropy principle that James put in 1957 as a main principle that consists of to write this Shannon-James entropy, or the people call Gibbs Shannon entropy, which is a functional of the probability distribution function. This is some prior of the system, and you have to take the extreme of this functional subject to some constraint. I will show you here. Okay? You start with this. You have to maximize the Shannon-James function subject to constraint, and in this way you can understand the maximum entropy principle as a statistical inference method to obtain the least biased probability distribution function from incomplete information. What is the incomplete information? The constraint. So, subject to one constraint, you take the extreme of this and you get one probability distribution function. If you have new information, you have to do an update of that and get another probability distribution function, and so on. So it's a very systematic way in order to obtain the probability distribution function, and the probability distribution function is all the information that you need to calculate any microscopic property. See that this is not, has in principle nothing to do with statistical mechanics. This is a general method when you have a system that has different states and you want to know what are the probability of each of these states. For example, in social problem, in economics problem, in any problem, you can put the problem in this framework and do these things. In particular, in physics. This is the canonical example, which is the canonical distribution. This is new for all physics students. You have to examine this functional subject to the normalization of the probability and to some constraint. For example, if you have a system which is in a heat path, this system, the average energy of the system is constant, is a number, right? But the energy change in time, but in average is a number. This is represented here. So the solution is via the Lagrange multiplier. In this way, you put the Lagrange multiplier. Here you have two Lagrange multiplier. You take the functional derivative and you get this expression. This is the prior, which in general is a plane prior, so this is 1, and this is the, you have to normalize this quantity. In this way, this is the normalization of this quantity, which is called the partition function, and the Lagrange multiplier, that is an unknown so far, is related to the constraint in this way. So you have to solve this equation, which is of course a transcendental equation, in order to get the value of the, this is one of the methods, the value of this Lagrange multiplier. And then the system, it's, you know everything about the system because you know this, you beta, h, the prior, that it would be 1, and you have everything. Of course, you have to be able to solve this integral and also this one. And then if you put this optimized, this final probability distribution function in the original functional, you get the optimized entropy for that system, and you, with this operation, you can relate this with the Helmholtz free energy, and obtaining the Helmholtz free energy, this is one of the fundamental equations of thermodynamics, so you know everything about the system. This is the way that this works, and this can be done in any ensemble because each ensemble has its own constraint, right? What's the idea of statistical mechanics, non-equilibrium statistical mechanics? The idea is the following, that you want to know what are the change in time of the different quantity, thermodynamic quantity, right? Supposing that this has some meaning. So the idea is the following in non-equilibrium statistical mechanics. You have a system in state A, then this is state B, and the system has some evolution in time following some path from A to B. Here is in equilibrium statistical mechanics, so here it's well defined, for example, the temperature, the energy, the pressure, etc. If here it's in equilibrium, it is in equilibrium also, it's clear but are different in principle, right? So the question is, it is possible to know what are these quantity in the middle? So each of these quantity is some kind of an average over sample. So one wanted to know how this average change in time, right? This is the problem of non-equilibrium statistical mechanics. So in this way, we want to know that. And in order to know that, we need to know how the probability distribution function change in time. Okay? Because here you have some probability distribution function that tells you what's the probability for each state, and here you also want to know what's the probability for each state, right? And to know according to this path. So the main quantity in non-equilibrium statistical mechanics in this, from this point of view is this probability distribution function in function of time, right? And if you go to the textbook, there are several methods also to obtain this, but there are no a principle, an axiomatic method. This appear just as different equation that always comes as partial differential equation for rho. For example, you have the derived equation, the Fokker-Planck equation, the master equation, the BBGKY hierarchy, etc. There are a lot of different equations which are for particular cases. Also the Boltzmann equation. So the question is why there is no an axiomatic principle. It's possible that we claim that it's possible, and with the method of maximum caliber you can derive all this equation in a clear way. Also in non-equilibrium statistical mechanics there are some relationships which, for example, the Jarzynski equality, Evans equation formula, good formula. So it is possible to find an axiomatic method to derive in a systematic way non-equilibrium statistical mechanics. This is the equation that it's a very ambitious question, but why not to try to answer, right? And the answer came also with James in 1980. He put forward that we can use this maximum caliber principle, which is an extension of the maximum entropy principle, in this way. That is very reasonable. We are in a system that is going from A to B. This system can take different paths according to the constraint of the problem, right? So, not any path, because according to the constraint, not any path to go from A to B is possible. But a subset of this path is this, and these are compatible with the external condition, with the constraint. So, the idea is we can go to a meta level and consider each path as a state of the system. So now the system is, all this is the system, right? This is the conceptual things. Now this is the system, and the different paths are different states of the system. Are different state of the system. So now we have a probability distribution functional. That is, a probability that depends of each path. So the question is, what is the probability of this path, of this path, of this path as a whole, not in each time, right? Conceptually, the problem is exactly as maximum entropy principle, because now these are the state. So we have to look for this rho, which is a functional of the path, right? What is the problem? That people like, or in the textbook, people need this rho that depends on the position at the time, right? So people want to know what is the probability of one state in this part. But we have now the answer. We have the answer of these things. Okay, so the program is the following: to obtain these things, and then from this, how to obtain this probability distribution function dependent on time, and then you match what every one knows or is already in the box, right? So, for example, if you have this probability distribution functional, then you can get an average of some quantity, but it's an average over all the problem by means of a path integral, right? So this is an integral over all the different paths compatible with the external condition. So you now are in the level of path integral. All the integral are path integral. Right? Okay. So what's the idea of MaxCal? And this MaxCal is max caliber. This is the idea of James, and caliber in the sense of the diameter of a gun, or say?
The barrel of a gun.
Sorry?
The barrel of a gun.
The barrel of a gun, right, the tube. So this is a tube of path. This is what you have to exercise, right? That's the name of caliber. It's nothing to do with the gauge or other things. It's caliber, just the diameter of this. Okay. We have to find the extreme of this meta-functional. Why meta-functional? Because this is a functional that depends, this S now, which is called C, depends of this functional. It's a functional, right? And it's a functional or a path integral subject to constraint. And for example, this can be the constraint this, and this is just an ampere of this constraint. If you play the same game with this meta functional, which is not difficult, completely analog to the MaxEnt, but now in functional calculus, you get, sorry, it's here. You get the following. For example, here it's the meta functional, and here you have a constraint. If this constraint is just a number, then the probability density functional of the different paths is in this way. And this is this quantity. Exactly like before. Before you have, for example, here the Hamiltonian and the energy, then the solution is this with the Hamiltonian here, and the Lagrange multiplier is with this quantity with the, in the case before was the energy, right? Exactly the same. But what's the difference here? But you can also have a constraint which depends on time, because in this case, time should be only another parameter that you take. And you can take the path integral over the path and the time another parameter, right? This is in detail in the paper, and we're not going in the detail, just the general idea. So you can have a quantity that depends on time. This is a path integral over this variable, and which is equal to a quantity that depends of time. For example, if you're going from A to B and the total energy is changing, so the total energy, the average of the total energy change as some function. This could be this function. And if you solve this, you get this quantity. So, in principle, you always can have this rho as a probability distribution function. Also, you can have this rho but by numerical method, some kind of Monte Carlo but with different curve. We did that. So, normal Monte Carlo is the different state, which are the position you move, and you have to fulfill some condition in order to accept or reject and in this way you can have what's the probability for each state. In this case, if you take different curve, you can do the same, and we did, this is the work of González and Sergio. They take different curve with this Bézier curve in a practical way, and they go from A to B with all the kind of curve that are compatible with some external condition, moving the curve and calculating what are the probability for each curve. So you can have this. But how you can get this quantity from this one, right? We call it this as a lysing process. You have to cut in some part this, because this quantity gives you the probability for each curve. But people want to know the probability of some value of the variable here at this time, right? So the question is how to obtain the expectation value of instantaneous quantity AXT, for example. XT is the value of the trajectory x in time t. So we want to have something like this. This is the probability of each path. This is the quantity. This is it's a function of the path. The notation here becomes cumbersome because and this is the time, and it's more or less one would like to have something like this integral, and in order to give you the average in order of time. This should be the generalization like this quantity. And how change this quantity in time. So this is performed by this time slicing equation, which you can have the probability of the value now, x would be the position in time, as an integral of this quantity, this rho that we already get, taking only the different path that cross one point, maybe in this way. Here are different paths compatible, but we have to take only the path that cross the position y in the time t. This operation is going in this way, but this is more general. The problem is how a path integral can be solved by means of partial differential equation. This is a problem that already people found in path integral a la Feynman, right? You have a path integral, and in fact, if you fulfill some condition, there is a formula which is called Feynman-Kac formula that transforms a path integral in partial differential equation, right? So, if you have a path integral, like in this case, we have at the beginning a path integral here for this quantity, we can transform this path integral in a partial differential equation, right? So, and in this way, we could obtain the continuity equation, the Chapman-Kolmogorov equation, the Liouville theorem, the hierarchy of this BBGKY, and this is the reason why the rho xt, so the partial distribution function in terms of time, you have partial differential equation to obtain that Boltzmann equation, etc. Here it's an explanation, at least for us. Perhaps many people already knew that, but at least for us, why all the expression for the probability distribution function times comes in the form of partial differential equation. And we found a systematic way to obtain this in different papers that I can give you, and also in this numerical way. So now we are in working on more practical problems, like for example this flux problem in the linear steady state case, etc. But working at the beginning with this maximum caliber method in order to show. So this is my talk. In the way that I presented it, it's not maybe it's not for new result, but it's a framework of non-equilibrium statistical mechanics, a general framework that allow you to get an insight of what is happening and what is the structure of the theory. But also you can get some practical things and maybe new kind of relationship that are in addition to the already known. That it's Sergio here also, so he can also answer your question.
Hello, there is time for a couple of questions. If anybody wants to ask anything, question.
I have two questions. One is for the first part, when you introduced temperature for spin systems. I was wondering, if I remember well, there are several ways to map the sphere into the plane and so get some sort of conjugate variables, Q and P, starting from the angular momentum variables. So like, I remember Villen transformation and the equivalent of Holstein-Primakov transformation. You mentioned the Nambu dynamics. And so what I ask is, depending on what kind of mapping you use, does the temperature change or not, the definition of the temperature? So the way you move from the angular momentum variables and the sphere towards the canonical conjugated variables Q and P, does affect your definition of temperature?
Let me explain this. First, just to clarify something, this name that we put the conjugate variable theorem is according the conjugate variable in the thermodynamic sense, right? Energy and entropy, pressure and volume, etc. According to that. So, and this is a theorem that maybe I can show you. It's very simple, that gives you an idea. Now, for how to get this formula in general, in the case of conjugated, now in the mechanic sense, PQ, in the case of conjugated variable, is simple. But if you have constraint in the system, then there is not clear what are the conjugate variables. That is the problem in the spin system. That because you have this constraint that the E square is 1. So you are not working in the full space of the conjugate variable, but in a subset, right? In a subspace. And in order to get the subspace, we found a general formula. According any constraint that you have, what is the, how to apply in principle, how to apply differential operator when you have constraint. Because in the case of spin, you have the Hamiltonian. Let me. And this operation is with this, for example, this Sx. So this operator is right, but if you apply this directly, this does not fulfill your constraint, which is that for example, you have here 3 variables and there are only 2, right? Because the spin move in this field.
Can't you just use a polar?
Yeah, if you use polar, there is no problem.
Okay.
Right?
Okay.
But not always it's so clear the constraint how to choose the exact coordinate.
Okay.
Yeah, that's one of the point of this formula.
Understand.
Yeah.
More questions?
I have another one.
Yes.
Sorry.
No, good, because you said 2 questions there.
So the second question, all the construction you presented with the path integral really reminded me a lot of the statistical path integral used to for studying, I mean the Feynman statistical path integral. So I was wondering, we usually think about quantum mechanics as deriving from classical 1 plus 1 dimension. So is in a sense what you are presenting us the opposite path, like, you know, having something that has 1 more dimension that becomes time. Okay, is good. Thank you. But comment as much as you want about it.
Yes,
I just wanted to understand it further.
Yeah, look, we are working on that. We are mixing up with all these things because this looks like Feynman mechanics, but without interference.
Yeah, exactly.
So it's very strange, but it's good because allow you to make some connection with the quantum mechanics as a past integral. In fact, for example, you can use this way to derive the Newton equation and the mass and some part of the, for example, for a free particle, and the mass appear as a Lagrange multiplier. And if this Lagrange, if the mass is an imaginary mass, you get the free particle in quantum mechanics. So maybe Sergio can comment on that because he likes this.
Okay, I'm not sure if I can add more to the last explanation, but yes, it seems like a real version of Feynman's path integral formulation of quantum mechanics with the real numbers in the exponent, like instead of minus I h bar with a real number, and then yes, you don't have interference and then the usual quantum effects, and you don't have the quantum amplitudes. You give directly the probability, the real number. Positive probability is this like a Feynman factor e to the action. It's actually the action of the classical system that you get in the exponent. So it is very suggestive that there is some connection between. Maybe there is some quantum version of this maximum caliber that will give you directly quantum mechanics. But we don't know what is the meaning of the need for complex numbers. So that's one way to so this formalism is almost correct to give you quantum mechanics, but we don't know why you need complex numbers.
I have a little question concerning the first part, because it's just like basic question, but you were able to show that your system temperature can be controlled in time, can be, let's say, concentrated, will not diffuse. And will this have an application, for example, on quantum computers or things like that? Because you can keep high temperature or you can also keep low temperature.
Yeah. Can be some application, maybe you know about that because your colleague there in that people are called thermal transistor. So the point now is how to you can make this gate by thermal transport, not just electronic transport or spin transport, but thermal transport. And this way it's good because you can, for example, this chain, this cesium nickel fluor, you can maybe tune the anisotropy. So you have a chain here, and you can put another chain here, and you can tune the anisotropy so the heat is transporting this way. You close that, and then again. This is what people are thinking in a particle system, for example, with the carbon nanotube. But that also can be done maybe with this. We claim that with the spin system. Yeah. This is more or less could be some application, but it's so far.
Of course. Okay, we thank you. Thank again, Professor Gutiérrez.